Today we're going to talk about section 8.1, which is estimating population means whenever we know sigma. So everything we're going to do in this section, we are going to assume that we know our population standard deviation sigma. So we will always assume we know sigma. So there are two different types of estimates that we can find for our population mean mu. So the first type of estimate is a point estimate. So what a point estimate is, it's simply a single value estimate that we can use for a population parameter. And in our case, we're going to talk about the population parameter mu. You can also estimate any other parameter. So you could estimate sigma. You can estimate rho, which is a proportion. You can estimate any parameter that you want to. For our purposes, though, we're just going to talk about mu, estimating the mean mu, even though the idea behind this is the same as for any parameter. So a point estimate is just a single value. Now for the population mean mu, the most unbiased point estimate that we have for our population mean mu is our sample mean x bar. So it makes sense, if we're going to estimate mu, the population parameter of mean, then it makes the most sense that we would use the sample mean to estimate that. So mu is going to be a sample point estimate. So that's going to be the point estimate that we use. Now the problem with this is you can take different samples and you get different means. So you'll have different estimates. So what we want to do is we want to look at something a little bit better, and that's going to be an interval estimate. So what an interval estimate is now we're going to have an interval or a range of values used to estimate a population parameter. Now we're still going to define this interval or build this interval based on our population mean or our sample mean. So we're still going to use that point estimate to build this interval, but the idea is we're going to get a better idea. We're going to get a range of values that our mean could be. And so let's say, for example, we have the point estimate x bar equals 29.6. Then we, doing some math that we'll talk about later, we end up with an interval estimate saying that the population mean mu can be is going to be somewhere between 27.5 and 31.7. So it's unlikely, if you're using just a point estimate, it's not likely you're going to hit the nail on the head. But using an interval estimate, we get a range of values that population parameter can be between. So we are fairly confident that our population mean mu is somewhere in this interval. So the question we need to ask ourselves is, how confident do we want to be that this interval estimate contains our population mean mu? So to answer that question, basically what we want to be is we want to have some level of confidence C. So what this level of confidence C is this going to be the percentage of all of our possible samples of some given size that are going to produce interval estimates that contain the actual parameter. So looking at this pictorially, then C is just going to be the area under the standard normal curve between two different critical values. So call these negative ZC or positive ZC. Your book also calls these negative Z alpha over 2 and Z alpha over 2, where alpha in this case is equal to 1 minus C. So alpha is the area that's remaining in both tails combined, and C is the area in between those two tails. So to find this, we would use the normal. You could use the standard normal table. So we've done how to find how to find a Z value in between. So how to find the Z value where we know the area in between two values. We've done that back in chapters 7 and 8, or sorry, 6 and 7. So we know how to do that. So let's say, for example, level of confidence is 90%. Then what that means is 90% of all the possible confidence intervals will contain the true population mean mu. Now what we're not saying there's a 90% chance that any one confidence interval will contain the mean mu. So there's not a 90% chance that the mean is in one single interval. This is saying if we were to do every single possible confidence interval, 90% of those confidence intervals will have the mean in it. So to find the critical value that corresponds to this, then we would do what we've done before. So our area in the middle is going to be our C equaling 0.9. So we've got a 90% area in the middle. That translates to 5% in each tail. So the 90%, 1 minus 0.9 gives us the 0.1. And then, so that's the area in both tails. And divide that by 2 to get 0.05. So that's how we get the area in each half. So the 0.05, 0.05. You then look up 0.05 on your z-score table. It's going to be equally between negative 1.64, 1.65. And since it's the exact middle of those two, then you add the two up and divide by 2 to get positive and negative 1.645. Now, we've done this math before, so I'm not going into too many details about it. Now, let me ask you this. Would you want to do this all the time? So for every single level of confidence C, would you want to have to do this math and do the inverse normal distribution every time? Probably not. So instead, we'll talk about a way in a minute. We have a table that we can find it. But first, we need to talk about what sampling error is. So sampling error is the difference between the point estimate and the actual population parameter value. So again, going back to what I was talking about before, if you have a point estimate, it is going to be wrong most of the time. It's not often that your sample mean is exactly equal to your population mean. It just doesn't happen normally. So sampling error, we're going to be wrong. So what the sampling error is, that's the difference between the point estimate and the actual population parameter value. It's just how wrong our point estimate is. So for mu, our sampling error is the difference x bar minus mu. And you can actually say in either order. So you can say absolute value of x bar minus mu if you want to. Just because of the fact that we know, okay, the mean might be bigger, so we might want to subtract in the opposite order. So that's what the absolute value lets us do, is it just makes it be positive. So mu pretty much is going to be generally unknown, which means we're not normally going to be able to find the sampling error. We normally cannot find this. And similarly, x bar is going to vary from sample to sample, so you're going to have a different sampling error from every single sample that you calculate of the same sample size. So what we're going to do is we're just going to use the margin of error, which instead is going to be, we're basically going to say, okay, to be some amount of confidence C, level of confidence C. So whatever we decide how confident we want to be that all the possible confidence intervals, what percentage of those do we want to contain the parameter? And so what we're going to do is we're going to say, okay, we're now just going to find the biggest possible distance between the point estimate and the value of the parameter. So we're basically going to take that sampling error and for a given level of confidence C, make it as large as we can make it. So we're typically going to call this margin of error E. So to calculate the margin of error E for a confidence interval for the population mean where sigma is known, assuming we have that given confidence level, C, so you'll be given C. And then alpha is equal to 1 minus C. Then, well, first off, we have to meet some conditions. So these conditions should look similar. So the first one, because we're assuming we know sigma, so the first assumption is going to be we know sigma. So we're going to assume sigma is known. We're going to assume we have a simple random sample. If you're using other sampling techniques, you end up with different formulas for this margin of error, and so it gets a little tricky. We're going to always assume we have a simple random sample for this class. Any other type of sampling is going to be outside the scope of this class. It's something you do in an advanced statistics class. So we're going to assume we have sigma, so we know sigma. We're going to assume our sample is a simple random sample. And then the next one should look very, very familiar to you. Either the sample size, n, is greater than or equal to 30, or the population is approximately normally distributed. So where do these seem familiar from? That's right, the central limit theorem. The reason why is because we're using the central limit theorem to find this margin of error E. So to calculate the margin of error E, it's going to equal to z sub alpha over 2, or in other words, our critical value of z, zc, times sigma x bar, so times the standard error of the sampling distribution, or the standard deviation of the sampling distribution of sample means. Or in other words, this is equal to our z sub alpha over 2, or zc, times sigma over square root of n. So again, because we're using the central limit theorem, we have to meet the requirements of the central limit theorem. So you have to ask yourself, is the sample size n greater than or equal to 30, or is the population approximately normally distributed, every single time before you can use this formula? So I mentioned before, you probably don't want to have to use inverse normal distribution every single time to find your z sub alpha over 2 or z sub c. Instead, we have a table that has these values already calculated for common values of c that we're going to be using. So this table is called the confidence interval critical values of zc. It's labeled table 3b on the last page of your course pack. Literally the very last page in your course pack is going to be this table. And so the page, to help you identify it quickly, it has a 31 on the top right hand corner as the page number, even though it's not page 31 in your course pack. That just comes from where I pulled this table from. So this table, it's on the very last page of your course pack, and it's going to be table 3, part B. And so I've also put this table here for a quick reference for you as well. So the way this table works is you just find your level of confidence C. So how confident do you want to be that out of all of them, the percentage of confidence intervals that contain it? So let's say 90%. And then just go across. There's your critical value of ZZC that you're going to use in that formula. So in this case, 90%. There's the 1.645 that we already calculated using inverse normal distribution. So that's all you have to do, is you just literally find your level of confidence C and then go down across and find your critical value on that same row. There's a table in your book you can use as well if you want to use it. It's very similar. It just has the alpha column in between also. So it has the level of confidence C, the alpha value that corresponds with that, and then your critical value. It's up to you which table you use. I'm going to use this table, but it's up to you. You can use either table you want to use. So let's look at an example of how we find the margin of error. So an economics researcher surveyed 40 employees from several grocery stores around the country, found the average number of hours worked by the employee was 29.6 hours. Let's use a 95% confidence level to find the margin of error for the mean number of hours worked by grocery store employees. We're going to assume the population standard deviation is 7.9 hours. So remember, first thing to ask ourselves, do we know sigma? In this case, we know the population standard deviation is 7.9 hours. So we know sigma is 7.9. And now we need to ask ourselves, does it meet the criteria for the central limit theorem? So is n greater than or equal to 30? Or is the population approximately normally distributed? So in this case, n is equal to, so we surveyed 40 employees. So n is 40. That's greater than or equal to 30. We answered yes to one of the two questions. Remember, for central limit theorem, you only have to answer yes to one of those two questions. So it's either n's greater than or equal to 30 or the normal distribution is approximately distributed. And it can be both. It doesn't have to be one or the other. You can have both of them be met and it still meet it because it meets one or the other. So in this case, we answered yes to the first question. Is n greater than or equal to 30? So we're good since our n is 40. So then now we know we can use the formula. So E is equal to ZC times sigma over square root of n. So to find this ZC, we're using a 95% confidence level. So C is 0.95. So we just go back to that table. So 0.95 is our level of confidence C. So our ZC, our critical value of Z, is 1.96. So critical value of Z is 1.96. So then E now is just equal to 1.96 times sigma, we said, is 7.9, divided by square root of 40 in this case. And so we do that and we get, rounding to one decimal place, 2.4 hours. So our margin of error in this case is 2.4 hours.